Right, so the 2022 physics exam's just been published, and looks reasonable enough so far. And I think probably the nicest question this year is question 6, the short questions, and you have to do 8 out of, and they've increased the choice to 8 out of 12. And in fact, they've given you an R as well here, so it's actually 8 out of 13, so it should be reasonably okay. So, question 6a. So, iron has a density of 7.87 gram per centimeters cubed. Iron sphere has a mass of 500 grams. Calculate the radius of the sphere. Well, the volume of a sphere is a 4/3 pi r cubed. And so density rho is equal to mass over volume. So volume is equal to mass over rho. So your mass over rho is equal to 500 over 7.87, and that's equal to pi r cubed 4/3. And so that got me 15.17. So r is equal to 15.17 centimeters. Seems reasonable enough. How many electron volts are in a kilowatt hour? Well, they're both energy, so it's the energy. Well, a kilowatt hour, so power, well, that's actually energy, it's not power. So a kilowatt hour is energy. So that's 1 kilowatt by 60 by 60 joules. So because power is equal to work over time, then the work or energy is equal to power by time. So we're multiplying it by time. So that's equal to 3,600 joules. And then an electron volt is given in our formula tables. So where is that? Electron volt here. An EV is equal to 1.6 by 10. That's a pretty small number. 10 to the power minus 19. Okay. 10 to the power minus 19, yeah. So pretty tiny number. So there's going to be a lot of electron volts in that guy. So the number, so how many electron volts? So the number of electron volts will be equal to the energy over the energy in 1 electron volt, which is going to be pretty massive. Okay, so let's see on our calculator there, 3,600 divided by 1.6 is 2,250 by 10 to the power of plus 19. So, and to put that in scientific notation, so the number of electron volts will be equal to 2.25 by 10 to the power of 23. So that's a huge number of electron volts. That's because 1 kilowatt hour is your standard use. So like that's putting a kettle on for an hour in a house. And then that's kind of the amount of, because electrons are so tiny, that's why the number is so big. Label diagram of forces on a piece of wood floating at rest. Now that is ambiguous. God. Okay, piece of wood floating at rest. Yeah, okay. No. Okay, so C. I am thrown by that. So I don't know what a student in an exam is going to be like. So we have a piece of wood floating at rest. Is it floating on water? We don't know. Force is acting on a piece of wood floating at rest. Okay, it's at rest, so it's in equilibrium. But okay, let's say, okay, it's floating on water then. I don't know, floating. God, I mean, okay, well look, anything you're certain of is that it has mg as a weight acting downwards. It has a reaction force or acting up. And that would be it, I would think. And they have to be equivalent if it's floating and it's at rest. Now I suppose I would put in a second diagram to maybe show it partially immersed. Okay, so that would mean you still have a weight, you always have a weight floating like that. And then you have, because it's floating, so you have buoyancy force upwards. And the buoyancy force then is going to be equal to the weight. And Archimedes' principle then would occur. So the volume of immersed is equal to the volume of displaced liquid, and the upthrust is equal to the weight of the object. So yeah, I suppose, look, that's probably a more accurate diagram for what they're going for, floating at rest. So buoyancy. Okay. Thermometric properties of a thermocouple and a mercury thermometer. Well, the mercury thermometer is fairly simple. It's the height of the column of mercury, and the thermocouple is the EMF. Transverse waves can be polarized. Explain what's meant by polarization. Well, polarization is, so normal light is a wave in many different planes, and polarization is blocking the light in one plane and allowing the light to go through in another plane. So if you can imagine, so waves are going in one plane and then also perpendicular to that, then you're blocking one of them and you're allowing the other one through. So an example would be shades that we wear as glasses, polarized glasses, which block out a portion of the light from the sun. Okay, sound intensity at a distance, this, okay, so sound intensity F. Okay, so sound intensity 0.18 milliwatts per meter squared. So the units kind of give you what sound intensity is. You know, it's power per area. At a distance 3 meters from the source, calculate the power of the source. So the distance is 3 meters. Okay, so what is the area? So you have this, it's a distance there. So the intensity is equal to power over the area. So if you need the power is going to be equal to intensity, which we have, by the area, and the area of the surface of that sphere is going to be given in the log tables in your area and volume section. So let's have a look. Area is 4 pi r, God, that's way too small for me. 4 pi r squared. Okay, so area is 4 pi r squared. So your power 4 pi and d is 3, yeah? So by r squared, which is 9. So it's equal to 0.18. Now it's millis, so 10 to the power minus 3, don't get caught out in that, by 4 pi by 9. Okay, so power will be equal to, let's run that into the calculator. 0.18 by 36 by 3.14, let's say. Yep, is equal to power is equal to 20 milliwatts. So just remember the milli there. Okay. All right. Now, transverse waves. Describe how an insulated metal sphere can be charged by induction using nearby charged rod. Okay, let's draw the diagram. So you have your rod. It's a metal sphere, insulated metal sphere, so that's insulation bit, and that's metal. Can be charged by induction using nearby charged rod. Well, you can charge the rod by, I mean, if it's a plastic one, you could rub it on a piece of wool or something, which gets your static charge built up. So what you'll do is you build up a charge on that. What that does is it induces an opposite charge on the metal sphere nearby it, and then you earth your sphere, remove the earthing, and you will be left with your charge on the sphere. So electrostatic induction. So you're inducing the charge so that a positive charge will induce a negative charge on that side of the sphere, which is attracted to this polar opposites, and that will be your charge on the sphere. Current carrying wire of length. Current carrying wire of length 20 centimeters. So length is equal to 20 centimeters. Let's get the units right. So that's 0.2 meters. Placed in a magnetic field. Smelling F is equal to Bill here. When a current of 55 milliamps flows, and where maximum force it can experience is 130 micronewtons. Calculate the magnetic flux and density. Okay, so yeah, it's true. F is equal to Bill. So you're trying to find B. So B is going to be equal to F over IL. So just as long as you keep your units, you should be fine here. 130 micros, so that's 10 to the power minus 6 over your current. Just be careful of your prefixes. 10 to the power minus 3 and 0.2. That is correct, isn't it? 20 centimeters. Yeah, it's 0.2. All right, so that should be okay so far. So the electricity questions tend to be fairly straightforward as long as you know the formula, and even if you don't, the formula are in the log tables. So divide that by what do we divide it by? 110, yeah. Well, 11. So yeah, we're going to divide that by 11, which is, so B is equal to 11.82. And now what's it going to be in terms of its suffix? Well, 10 to the power minus 6 over 10 to the power minus 3. So it's 10 to the power of minus 3 Tesla. So it's important to get the units right. And Tesla now being made by Elon Musk as cool cars in honor of the great Tesla himself. So 11 by 10 to the power minus 3 Teslas there. Okay. So tungsten cube of side 2. Tungsten cube of side 2 to resistance. Okay. Cube. Okay, so it's a cube. Great. So we're given the dimensions of it. That's nice. So we can be able to get the volume. Has a resistance of 2.8 micro ohms. Calculate the resistivity. Okay, resistivity rho. We saw that in the log tables is equal to yeah. Picked it out of the log tables, RA over L. So rho is equal to RA over L from the log tables. So you're asked for the resistivity of tungsten. Okay, so cube of side 2 is the resistance of this resistivity. So, okay. Calculate the resistivity of tungsten. Okay, so your side is 2 centimeters. So x is equal to 0.02. And okay, so your area is equal to, so how many centimeters? It's going to be 4 centimeters squared. So it'll be, okay, 2 to the power of 10 to the minus 10 minus 2. So square that, and it's equal to 4 by 10 to the power minus 4 meters squared. Okay, so the side is 2 by 10 to the power minus 2 meters. So we're trying to keep it in SI, and area is that. Okay. And okay, so rho is equal to 2.8 by micro, which 10 to the power minus 6, by 4 by 10 to the power minus 4, over length, which is 2 by 10 to the power minus 2. So it's equal to, well, 2.8 by 10 to the power minus 6 by 2 by 10 to the power minus 2. So what's that? 5.6 by 10 to the power minus 8. Now what are the units of that? Well, okay, that'll be ohm meters, because it's ohm meters squared over meters, ohm meters. Okay. Right. Hij. Okay, so J, Bohr's model of the atom explains emission line spectra. So a lot of people might have left that out, but if you, emission line spectra are in terms of quanta. So you'll see that if an electron moves from a higher energy higher energy rotation around the electron to a lower energy rotation around the electron, it releases an amount of energy in quanta, so n times a quantum of energy, and that then can be seen in the line spectra in terms of different colors, and each one is different. So it's packets of energy. So it showed that they're a quantum of energy and not a kind of a continuum. Thermometric emission in X-ray tubes, a lot of people might have left that out as well. But a lot of people would have left that out as well, pair annihilation. But this one would be the easy one to do then. So that would be, so L, draw the symbol for the AND gate. So the AND gate has a symbol like that. So AB and the output. Write out the truth table. So the truth table for AND looks like this. So you put all your possible combinations of A and B, and then the output associated. So 0 and 0 is 0. So the output is only going to be 1 if A and B are 1. So that's the case where the output is 1. These ones are all going to be 0, because for an AND gate, it's only if both are, if A and B are 1, then the output is high. Okay, so let's have a review of that. So let's see the accessible ones there. Well, the AND gate is pretty nice. So that's 1. Tungsten cube should be all right. That's 2, 3, 4, 5, 6, 7, 8, 9, 10. So there's 10 there. So 8 out of 10 there should be reasonably okay, I think, to answer. And the possibility of getting another 1 or 2.